Okay, once we come back to this this interface here, that means we already create these models. All right. So the next step is the next step of the assessment, we have to go through the next procedure, which is the code requirements. So we can check before we go through that. Let me check this model. Everything looks fine, looks brilliant actually. Then we go to the code requirements. Okay, if we go to these code requirements, we already pre-select the code, which is ASCE 41. So the first thing is, as what I mentioned, we are based on performance-based seismic methodologies. We have to select what's the performance levels according to ASCE 41. So we can select what kind of performance objective you're looking for. Either if you're familiar with ASCE 41, you know that there is what we call basic performance objective for existing building, BPOE. These are most basic, most common performance level we choose. Or if you want, based on your different client requirement, you might select enhanced objectives. Okay, you can select any type of enhanced objective. You will select from here. Or you can go into limited objectives. This one is more specific cases. But in our exercise today, we go to the most basic one, the basic performance objective for existing buildings, which is a BPOE. Basically, the BPOE is look into two seismic level, which is in this case will be BSE 1E, BSE 2E. All right, these two selection here. All right, and then at the limit state is basically the life safety and also the collapse prevention. All right, which is these two limit state already selecting here. All right, so this is our first setting for our performance level. The next one is the analysis type. In our current version of Seismic Build 2020, we only got pushover analysis, but in our future version, we're going to include all these 4 procedures. So for today, I will only look into the pushover analysis. All right. So for the setting here, we can select how many load cases or load analysis to carry out. If you select all, basically got 168 cases. It's quite a lot. Or you can choose either basic configuration combinations. It means you already select these 8 cases for you, or you can select based on the specific code. All right. In this case here, like you can select ASCE. ASCE will be the analysis case number 17 to 24. All right, so it will based on the load patterns will be not uniform, will be model. All right, the combination, the direction will be in the X or in the Y direction. Usually initial state, I would prefer maybe you carry out all the 8 cases for the stage 1. Then when you move into stage 2, you know that after you carry out stage 1, you know that which load cases or analysis are critical. Then after that, you apply the retrofitting. In the stage 2, you will go more specific combination. So in the initial stage 1 here, I will select all the 8 cases. Then the next one is the knowledge level. Knowledge level is based on what is the level of knowledge you have for your structures. Is whether you get the detail directly from the drawings or you carry out some non-destructive test, NDT test to get some data. Usually the more preferred is usual, but you can choose minimum. But if you can see that if I try to choose minimum according to this clause 6443 in ASCE 41, when nonlinear procedure are used, data collection consistent with either usual or comprehensive knowledge shall be performed. So he asked me whether you want to continue or not, whether you want to choose minimum or usual. But this one is based on your condition. So in this case here, maybe I will choose, let's say, minimum as our case, because we don't have any more information. I will choose minimum. For seismic action, this one is 100% from the ASCE 41. It's a code-based spectrum. We can either code-based or usual define your spectrum. Up to you. Okay, you can define the spectrum that you recorded based on from what code. But in our exercise here, we're going to use a code-based spectrum. And the setting, I will keep it the same. The soil type, you can choose maybe either C or D. Maybe I choose C in this case. All right. And then the next one will be static actions. This one coefficient will be the fix and the check. Finally, the last tab will be the check. What kind of check we want to carry out? In this example here, I will create 3 check, maybe member core, shear, member shear forces, and interstory drift check. Okay, so once we done all our setting, we can start to do our analysis. The first analysis, what we do is the eigenvalue analysis. You can see that is before you can start to do the analysis, you have to do this. You have to save the model. So we create yes. Okay, it saved the model already. Now we want to carry out our first eigenvalue analysis. So we run the first analysis. So once you complete the analysis, you will come up with this this message. All right, it will call you to double check the model to verification of the connectivity. So we can see the result for the eigenvalue analysis from here, from this button. It indicates here there's a 10 different fundamental mode of your models. All right, so you can even carry out a 3D models in this case here. Okay, it's 3D, animate the 3D model. In this case, what is showing here is the first mode. This one is the second mode. Okay, you can increase the deformation if you want to see more obvious. Okay, this one is our second mode. This one is our first mode, the third mode, fifth mode. So basically is we want to check whether the connectivity is okay or not okay. So it looks at everything looks like intact. There's no any separation occur. So we know that this model looks fine. Okay. So some of the result that we calculate is from our eigenvalue analysis is most important. We carry out the model period and frequency. Is something we carry out the model participations factors. Is all from this section. All right. And the effective model masses is calculated for you all the three directions, the percentage of it, and the step output and analysis log. All right. So once we have carried out the eigenvalue analysis, we can move on to the next step, which is our pushover analysis. All right. So we go to the pushover, we run the analysis. So because just now we select 8 cases, so basically it will run through all the 8 cases here. All right. So in terms of viewing the you can choose the first one, see only essential result. This selection actually is the fastest, but you can also do the second one is the real-time plotting. This is something will be more interesting. Is for real-time plotting of the pushover curve. All right, for each of the load case. In this case here, now we're plotting pushover analysis case number 18. Okay. You can see that is you can see the progression step by step development of the pushover curve, which is the base shear versus our target our displacement based on the control nodes. Okay, and another step what you can do is the third one is the real-time drawings of the deformed shape. This one will be more interesting. You can see that in this case here, you see this load combination is push is negative x direction eccentricity of y. You can see how the pushover of this building happen in real time. This is how the pushover of these real buildings. Okay, you can see that if you look into plan view, is x and the y with eccentricity in positive direction. So it caused the building to be slightly torsioned a bit. So this one is negative x. So again, push in these directions. And negative eccentricity push in this direction. So will be some slightly torsional. Okay, it gives you some idea how it push over of this structure looks like. This one now is pushing in the negative x direction. This one is y direction. Okay, you can see that the structure how it push in 3D view. And analysis number 5 is a combination in y direction, which is y direction positive, and x direction positive. That means it's eccentricity in x and main direction in y. So you can see that is how the deformation looks like of this pushover to these buildings. Okay, now analysis case number 6. This one is a positive again with negative eccentricity x. As what I said just now, for the first stage, usually I will select 8. After maybe we go through the chat later on, we define which of the analysis critical case. When we go to the second stage, we can maybe run maybe 4 or 2 cases will be more than enough for our case. All right, so the easiest way to maybe if you don't want to go through a real time, you may save some time, you can select the first option. It will run the analysis slightly faster, but you won't be able, of course, you won't be able to see the deform and also the pushover curve. You can see the analysis running below. Then you can see that there's an incrementation. LF means by the load factors. This value convert means is convert the results. All right, so you can see every stage is able to convert the results. So this one is analysis number 8, our last load combination analysis. Okay, so once everything is finished, it will come up with this message. All your analysis have reached the values, the analysis. So first thing is what you can do, you can show the results. This is the easiest way. You can click one, you can see all your results. You can come up from this bar here, you can view for each of the analysis, what is your results. Like what is shown in this curve here is a base shear, your pushover curve, your base shear versus the displacement. Okay, and also including the target displacement calculations for each of your limit state and also for your maximum. All right, so you can see that in this drawing here, there's a 2 dot here, one orange color, one is the red. The orange color representing this line here, representing the target displacement based on the limit state of life safety. And the red color here is representing the limit state of collapse prevention. This is the value of target displacement we already calculate for you. And this is the structure, these are our limit state values. So you can select from this analysis, you can select the Y, okay, any analysis you prefer to, all right, any load combinations, okay. And then you can go into, look into, I will try to go into the main one first, all right. The second one is the deformed shape. I think this one will be quite useful as well to check through, like for instance, like code check, you can look into the formation of the plastic hinge, all right. So in this case here, like let's say I select this example, this load combination Y at negative Y here, all right. So what you can do is you can see that you can increment stages by stages. You can see that it let you show you the stages of the formation. You can see that at load factor, somewhere around load factor case number 17, there's still no any failure happen on this building. But once you increase to the next one, you can see there's a start to formation, what we call formation of plastic hinge happen on these buildings. And the building start to change some colors, am I right? So, and then you can continue, you can see that, let me continue. You can see continue, push and push. You can see every stages, which part of the building start to yield. This is where the formation of the plastic hinge. So in this particular concrete wall, the bottom hinge start to form, then after that form at the top. All right. And then you can further increase the stages load factor until you can see that this corner of the column will be distressing. So if you're thinking about strengthening, you might think about these two components will be something quite critical. You need to think about it. Then you can continue push until the end to be more failure happening, you see. Sure, and also the formation of plastic hinge. I think this function is quite useful. Let you see every stages of where is the critical elements and also the formation of the plastic hinge for you to identify which part of the structure are critical. And also, I will want to show you this one as well. We can also plot the bending moment and shear force diagram. And this one is a bending moment here or shear force here. All right, let's choose the moment, and then we can choose only for, let's say, horizontal member only. Okay, so you can choose much more smaller scale. Don't want to be overcrowded. So then you can choose in this particular member. You click, it can show you the view in 2D or 3D. And then you can see the increment of the, in this particular member, the moment and the shear force in the increment of the load factor. All right, very simple. Okay, let us now move on to the next one, which is the check. The check here is basically to check our member in relation to the code-defined methodology. This is the most important one, to let us define whether which part of the buildings are critical according to this performance level that we're choosing. So you can see that it's based on the limit state of life safety here. This Concrete walls are struggling a bit in the red color. That means the ratio is quite high. Collapse prevention, let's check. Seems to be quite high. So then what we can do is we can look into the performance levels. We can select the field members, select the performance ratio. So you can see that is based on this limit. If the value less than 1, it means it's okay. But in this concrete wall, it's 1.22, so it's quite high. So what you can do is you can also got an option to choose the whole member, the whole floor. You can choose maybe only for the first floor. It will be less crowded, and maybe only choose for the column. It gives you some overview about your first floor column. So you can see that is this whole first floor here. You can see all the ratio, or less than 1, it looks okay. But in this building here, notice that is the result is this wall is 1.22 and this column here is 0.81. It's very close to 1. All right. So in terms of strengthening, it really can help you to decide which of the members are critical, are more concerned about. All right. So, and the second one, we can also check for the member shear force. Okay, member shear force, just now you can see column is okay. You can pass all the shear check, no problem. Let's check for the beam. All right, it looks like the two of the beam value here, the value ratio are more than 1. So it's showing some value. So we can maybe select here, choose all the members. You see more clear without the values. So it looks like from this exercise here, we notice that is for beam shear, these two beams seems to be failing for the shear failures. So it's something that we want to prevent shear failure from happening. So strengthening need to be taken out of these two members. Okay, so let's see the shear failure member and performance level. Okay, these are the values. The life safety, let's check the life safety values. This for life safety limit state, this beam seems to be quite okay. But these values are very, it's more than 1. So definitely this beam we need to do strengthening. This beam also need to consider that. Okay. So once we have done that, you can see I have completed my stage 1, which is this stage 1 here. I have successfully identified which of the beam elements are critical. Like for member shear force, we realized that these two beams are critical. And member core rotations, basically these shear walls, and also maybe I will consider this strengthening of this column as well. All right, so now I complete the stage 1 already.